So now with that said, it's my great pleasure to introduce our distinguished speaker today, Professor Qingfeng Zhang, and we already see his faces. The title of this webinar talk is Dispersion Engineering for Frequency Diverse Real-Time Microwave Imaging and Sensing. And let me first introduce Professor Qingfeng Zhang. Professor Qingfeng Zhang obtained the bachelor degree from University of Science and Technology of China in 2007 and PhD degree from Nanyang Technological University, Singapore in 2011, all in electrical engineering. And from 2011 to 2013, he was with the Polytech Montreal, Canada as a postdoctoral fellow. And since December 2013, he joined Southern University of Science and Technology, Shenzhen, China, where he's now a tenured full professor, vice chair of Electronic and Electrical Engineering Department, and director of Shenzhen Engineering Center for Electromagnetic Non-Destructive Detection. Dr. Zhang is an IET fellow and IEEE senior member, and his research interests are largely in emerging novel electromagnetic technologies, where he has a special interest in dispersion engineering at microwave and millimeter wave frequencies. He has published over 130 SCI journal papers, including more than 90 IEEE journal articles. And Dr. Zhang served as the vice chair of IEEE Antennas and Propagation Society, Shenzhen chapter, the lead guest editor for Spatial Cluster, Smart Surfaces, Antennas and Propagations for Integrated Sensing and Communications in IEEE Antennas and Wireless Propagation Ladders, and also the TPC chair of 2021 CSQRWC. And he was also the recipient of ERSI Young Scientist Award and ACS Young Scientist Award in 2018. And now, without further ado, let's welcome Professor Qingfeng Zhang for his interesting talk. Thank you.
Okay, thank you, Professor Song, for your introduction. So let me share my screen. Can you see my screen?
Yeah, I can see it.
Okay. Okay, so everyone, hello everyone. My name is Qingfeng Zhang from Southern University of Science and Technology, China. Today my talk is dispersion engineering for frequency diverse real-time microwave imaging and sensing. So firstly, I want to acknowledge all the contributors for this work. Dr. Zhang Ke, Zhou Hongxin, Ma Dingfei, Liu Baiyang, Guan Dongfang. They are former members from my group. And Mr. Du Jiacheng, Xiao Shuguang, Xu Wentao, Chen Xinghao, they are PhD students. And Mr. Wei Yifei, he is the master student. And Mr. Nie Mingyu and Zhang Jiarui, Ms. Zhang Jiarui, they are undergraduate students. I also want to thank all the collaborators, Professor Ross Mersch from Hong Kong University of Science and Technology. We have co-supervised several PhD students in the past years, and Professor Chi-Ho Chen from City University of Hong Kong. We are also co-supervising PhD students, and Professor Heng Wang from City University of Hong Kong, Professor Da-Qin Zhang from Peking University, and Professor Kui-Wen Xue from Hangzhou Dianzi University. Okay, so this is outline for this talk. Firstly, I will introduce the motivation of frequency diverse imaging. And the second part is the design principle and the figure of merit. And then I will introduce the dispersion enhancement techniques for some novel structures. And in the fourth part, I will introduce some imaging and sensing examples. Finally, I will conclude this talk. Microwave imaging and sensing has wide applications in different areas. For instance, consider weapon detection, automotive radar, 4D imaging, medical imaging, and integrated sensing and communication. Integrated sensing and communication, so-called ISAC, is one of the potential technologies for 6G communication. ISAC is defined as a technology that integrates sensing and communication functionalities to achieve efficient usage of wireless resources and to mutually benefit each other. So within this definition, we have two parts. One is communication-assisted sensing. We use wireless network to perform sensing functionality. The other one is sensing-assisted communication. With the sensing information, we have better knowledge of the wireless communication channels. So this can help on the beam training, beam tracking, and beam prediction. So ISAC is a cross-discipline topic involving many different areas. For the communication scientists, they work on the signal processing, waveform design, network optimization, resource allocation. And for the electromagnetic scientists, actually the goal is very simple. We work on the antenna innovations for this ISAC application. Then let me introduce some requirements for the sensing antennas in this ISAC application. Firstly, the antenna should be compatible with the communication architectures. For the communication, the bandwidth usually is very small. For instance, 5G NR1, the channel bandwidth is less than 100 megahertz. So the relative bandwidth is less than 2%. So we should use this narrow frequency band to perform sensing functionality. According to the radar knowledge, we know the range resolution is usually proportional to the bandwidth. So with this narrow frequency band, the range resolution is very low. We cannot change this. But how about angular performance? So this is determined by the beam forming or beam scanning performance of the antenna array. So the antenna should scan a wide angle with a high gain. So this can realize a wide field of view and a good, very high angular resolution. And also the scanning speed should be very fast because the real communication channels are always changing. For instance, in the indoor communication, if someone is walking around this antenna, the real channels will be always changing. Finally, the antenna should sacrifice less communication performance in two aspects. Firstly, it should save the MIMO channels because MIMO channels are used for the communication. If we occupy the MIMO ports or transceivers for the sensing, it will sacrifice the communication performance. So we have a trade-off between the sensing and the communication. And secondly, it should save spectrum resources. I think this is straightforward because spectrum resources are expensive in communication. So it means the spectrum occupation for the sensing should be as small as possible. Okay, then let's look at typical imaging and sensing problem. Usually we have some antenna array. It sends out the electromagnetic wave to the scanner, and then we the spectrum wave using this the sensor array. The question is how do we collect this spatial data in this 2D plane? Once we have this data, we can use some algorithms to reconstruct the unknown object. The most simple way is use the MIMO or phased array. This is an expensive solution because it requires lots of transceivers and ADC. The second way is mechanical scanning. We only need one single transceiver and ADC. The drawback is has very slow speed. And then we have also the electronic switching. We can design a switching matrix to switch all of these antenna one by one. In this case, it will become very complicated if we have a lot of antennas, and it is also lossy for the switches. And then the question is, can we get a new architecture featuring a simple and a low-cost system? And also it has very high speed in capturing the spatial information. Then we have this frequency of diverse imaging. It was proposed by David Smith's group in 2013. So originally, they proposed to use the metamaterial structure, as you can see here, to produce dispersive fields to shine this unknown object. So different frequencies has different field pattern. So these different frequencies represent different measurements for this unknown object. So finally, you will have a linear equation to solve this problem. So this metamaterial structure can be regarded as the magnitude dispersion because it employs randomly distributed resonance cells. So all of these small cells has different resonant frequency. They are randomly distributed. So as the frequency changes, the magnitude of these fields above the surface will change. We have another category. It's called a phase dispersion. In this case, the magnitude does not change with frequency. It's a non-dispersive magnitude. Ideally, the magnitude is uniform. It does not change. But the phase change with frequency. So this will lead to the beam scanning. We call this as a frequency scanning antenna. The leaky wave antenna is one of the typical antenna in this category. So in this talk, we will focus on this phase dispersion. Let's compare the magnitude dispersion and the phase dispersion. So for this magnitude dispersion, it requires random magnitudes to achieve frequency diversity. So it has broad beam and a low gain. So the signal to noise ratio in the imaging case will be very low. So it is applicable to very near field applications. In contrast, for the phase dispersion, the beam can be directive with high gain. So the signal to noise ratio is very high. So such a technology can be applied to both near and far field applications. Finally, let me summarize the benefits of frequency diverse imaging. It has a very high speed versus mechanical scanning or other reconfigurable architectures using the switches or varactors. The capture speed is almost in the level of nanosecond, so almost real time. Low cost and a simple architecture versus MIMO or phased array architectures. And also flexible control in steering the beam using frequency. And it is also a very promising technology for ISAC application in three aspects. It is high-speed beam scanning, and it saves MIMO channels using the single input, single output SSPP. And it also saves the spectrum resources by using the so-called extremely high dispersion antennas, which can scan 70 degrees within 40 megahertz bandwidth at 4 gigahertz frequency band. It's 1% relative bandwidth. So we need to design this kind of very spatial antennas for this ISAC application. Actually, this is very challenging because for the conventional leaky wave antenna, usually it requires several gigahertz bandwidth to scan the beam. So that's why we need this dispersion engineering technique to design some novel structures to scan the beam within a narrow bandwidth. In this talk, we will introduce two different imaging scenario. One is called radiative imaging for the near field and far field application. In this case, we designed the fast scanning antenna. And the second case is the guided wave imaging for very near field applications. In this case, we designed a dispersive transmission line and discrete resonators. Both of the two cases are frequency diverse imaging. We will cover the two different imaging scenarios. Okay, let me introduce the design principle and the figure of merit for this design. So here, this figure shows the imaging scenario for the radiative imaging. So we have two antennas. One is the transmitter, one is the receiver. They are frequency scanning antennas. So the S21 is the from transmitter to the receiver. The signal S21. Here we use the V omega to express this S21, and it is the integral of three components. ET and ER are the fields of these two antennas radiate into this imaging domain. And the rho is the reflectivity of these each pixels in this imaging domain. After discretization, we can use this matrix to express this problem. V equal to H rho. V is the received signal at the port. It means the S21 signal if we use VNA. And the rho is the reflectivity at each pixels of this imaging domain. And H is the measurement matrix. It is the multiplication of ET and ER. So for this measurement matrix, it has all the information of this antenna. Later, we will use this measurement matrix to evaluate the performance of this antenna. Okay, once we have this linear problem, this rho is the unknown that we need to solve. The V is the measured signals S21. So to solve this inverse problem, we have a lot of algorithms to solve this. For instance, the compressive sensing on the sparsity prior knowledge. So here we use the twist algorithm. It is one of the most popular compressive sensing signal processing algorithms. For the guided wave imaging, we replace this antenna with a transmission line. It's a guided wave transmission line. So we place some scatterers above this transmission line. The goal is to reconstruct the positions of each scatterer. So it's a 1D imaging. We can also extend this to a 2D imaging by place a lot of transmission lines in parallel. So by using the transmission line equations and the Born approximation, we can also get this linear problem, gamma equal to H rho. So gamma is the total reflection at this port, S11, and the rho is the local reflectivity at each pixels along this transmission line. H is the measurement matrix. Okay, so these two imaging scenario has similar linear problem. And then the question is, how do we evaluate the performance of these transmission line or antennas in the case of a frequency diverse imaging? So we should define a figure of merit in this a new application scenario. The first way is we can directly evaluate using this measurement matrix H, because this H has all the information of this electromagnetic structure. We perform the singular value decomposition on this matrix. So decompose into three matrices, U, sigma, and V. The singular values is stored in this sigma matrix as the diagonal entries. So this figure shows a singular value distribution of a typical example. So it has 100 measurements, but we can see here the non-zero singular values are less than 15. So this means although you have 100 different measurements, the effective measurement is only 15. Most of these measurements are redundant. They have zero singular values. So we can use this SVD analysis to evaluate the effective number of measurements for the electromagnetic structure. We can further define our sensing capacity in analogy with the MIMO communication using the channel capacity. So here, lambda is the singular values that are calculated using the SVD analysis. The P divided by N is the signal to noise ratio. So we can define this capacity C here. So we establish a one-to-one correspondence between the MIMO communication and the imaging and the sensing. So here, the channel matrix in communication corresponds to the measurement matrix in imaging. Okay, so these non-zero singular values in communication means the independent channels for communication. So here, in the case of imaging, all of these non-zero values means the independent interactions between this antenna and this object. So this vector in this U and V corresponds to the channels in the communication. In the imaging case, the vectors here corresponds to the interactions. Okay, so we have a unified point of view to look at the communication and imaging. Then let's look at the relation between the sensing capacity and the dispersion and the loss. So here we show three different transmission lines with different dispersion. So TL1, TL2, and TL3, we increase the dispersion from 1 to 3. So this shows the dispersion curve. The dispersion increase from 1 to 3. And we can see the mode number will increase as we increase the dispersion, and also the capacity will increase. So this shows that the sensing capacity is proportional to the dispersion in this frequency diverse imaging application scenario. And this figure shows the effect of loss. So the first figure shows the lossless case. If we don't have any loss, this figure shows the singular value distribution. And as we increase the loss here, we can see the singular value drop. So the capacity will drop, right? Further increase the loss leads to a further drop of the singular values. So as a figure of merit, so we need to enhance the phase dispersion of the transmission of antennas. And meanwhile, we should decrease the loss. For the antennas, usually we wanted to describe this FOM using some far field parameters, for instance, the beam angle. So here we also define a scanning rate. It is defined by d theta divided by d omega. D theta is the beam angle change, right? So this scanning rate will tell you the sensitivity of this angle with respect to the frequency. After some derivation, you will see that this scanning rate is proportional to the phase dispersion of this transmission or antenna. So finally, we can use the scanning rate as a figure of merit because it is proportional to the phase dispersion. So we have to the same antennas. Then let me introduce the dispersion enhancement techniques, since high dispersion is preferred in this application. We will introduce three different techniques to enhance the dispersion. The first technique is called delay feed. So we insert some large delay element into the feeding network of the leaky wave antenna. So the phase dispersion is inversely proportional to the VG, the global velocity. It's proportional to the delay of each element. So by inserting the large delay element, the dispersion will be larger, so the scanning rate will be larger. The second technique is called dispersive feed. So we directly design some artificial transmission lines with high dispersion curve. So for instance, using the spoof surface plasmon structure, if we look at this dispersion curve, as the frequency is close to this region, close to the surface plasma frequency, this is high dispersion region. So if we use this region to design a leaky wave antenna, it will has a very large dispersion or high scanning rate. The third technique is coupled resonator feed. So here we use high quality resonator to feed these antennas. As we know, for the resonator, the phase changes quickly with the frequency at the resonant frequency. So we can use this feature to enhance the dispersion of the antenna array. So I will introduce these three techniques one by one. First technique is delay feed. So this is very straightforward. So this figure shows a conventional leaky wave antenna. It's a series stop leaky wave antenna. And then we insert this delay element. Here, this is a complementary stop slot element. And this is a C-section element. Both of these elements are all-pass network. They can increase the delay and enhance the scanning rate. So these three figures show the scanning rate enhancement from 3.5 within 100 megahertz to 8 degree within 100 megahertz. And later we improve this structure. Instead of inserting this to the feeding network, we directly design this all-pass network as a radiator. So here we choose this complementary stub slot structure as the basic element. So here this structure has a microstrip stub and also has a complementary slot on the ground plane. If you design these two with the same dimension, they are complementary. In this case, it will be an all-pass network without any radiation. As we have a mismatch between the two dimensions, we will introduce some leakage. So this will become a leaky wave antenna. So this figure shows the leakage versus different mismatch. So as we increase the mismatch, it will transit from the guiding wave to the radiating modes. Okay, so we also check the radiation of this field pattern. We see that the radiation is contributed by the odd mode. It means this slot mode of this element. So these figures compares three different cases. We want to verify the relation between the scanning rate and the dispersion. So here we use three different group delay elements to produce three different dispersion leaky wave antenna. So as you increase the group delay, the phase dispersion will increase, and then the scanning rate will increase. But if you look at the efficiency here, you can see the efficiency will decrease. So we have a trade-off between the scanning rate and the efficiency. So as you increase the scanning rate for the leaky wave antenna, the efficiency will get low. That's the price you need to pay. So this figure shows the fabricated prototype, and this is the scanning performance. It can scan 30 degree within 200 megahertz bandwidth. This is another technique using the meander transmission line. So here we coupled a lot of meander transmission lines to form this leaky wave antenna. So meander transmission line can increase the delay of each element. Here we also using the matching stub in each element to suppress the open stop band at the broadside. And here, this figure shows the scanning performance of this antenna. It can scan 180 degree within 1.1 gigahertz bandwidth. And also, it has a stable gain around 11.5 dBi. Okay, let me introduce the second technique. It's a dispersive feed. In this case, we design some artificial transmission line to feed this leaky wave antenna. So for instance, here, this blue line is the dispersion curve of transmission line. And then if we select this high dispersion region and then shift this to the faster wave for the leaky wave radiation, then we can design a very high scanning rate leaky wave antenna. This shift can be done by periodically modulate the light profile to generate the space harmonics. So as you can see here, by introduce a periodic modulation of D, you can generate the space harmonics. And if you look at dispersion, as you introduce this space harmonics, the slope of this beta does not change. It means the dispersion does not change. So as you shift this dispersion curve to this faster wave region, the dispersion does not change. So the scanning rate of leaky wave antenna is determined by this dispersive transmission line. It means if you wanted to realize a high scanning rate leaky wave antenna, you need to design a very high dispersion slow wave transmission line first. A lot of candidates can be used to design this kind of high dispersion transmission line, for instance, spoof surface plasmon and global line. So they have this kind of a similar dispersion curve. You can select this high dispersion region and then shift this region to the faster wave region for leaky wave radiation. I will introduce two examples to illustrate this technique. The first example is hybrid SRW spoof surface plasmon structure. So here, this figure shows the configuration for this hybrid structure. Basically, we cut some high density slots on the top surface of this SRW waveguide. You can produce the spoof surface plasmon effect. If you look at the dispersion curve, it's a combination of these two waveguides. So you have a lower cutoff frequency because of this SRW. You have higher cutoff frequency due to this spoof surface plasmon effect. When you change the parameters of this slot, you can change the cutoff frequency of this spoof surface plasmon. So we can shift this high dispersion region to the faster wave region to generate the leaky wave antenna. So this shows the configuration of this leaky wave antenna. So we periodically modulate the width of this slot. So this is uniform, but here we periodically modulate this profile. This way produce the space harmonics to radiate a leaky wave. This figure shows the radiation patterns at different frequencies. So it can scan 35 degrees within 400 megahertz bandwidth. This is a very early design from our group. Later, we have a second design. So this is a glide symmetry SSP leaky wave antenna. For the conventional SSP structure, we know we have an open stopband here between the mode 1 and mode 2. So as we shift this high dispersion region to the faster wave for leaky wave radiation, this stopband will reflection or the loss. So we wanted to close this stopband here. Then we propose this glide symmetry SSP structure. So by using this glide symmetry, we can close this stopband, make the mode 1 and mode 2 connected with each other. So that's the functionality of the glide symmetry. The glide symmetry is defined using this figure. This compares the longitudinal symmetry and the glide symmetry. So as we flip this the structure, we should shift by half a period of this of the whole period. This figure shows some examples of the glide symmetry structure using different implementation. In this design, we use the single conductor SSP structures to produce this to implement this glide symmetry. So as we change dimensions of this SSP structure, as long as it follows the glide symmetry structure, you can see the dispersion curve. It's always has no stop band here. So mode 1 and mode 2 are always connected with each other. And then we also look at the field distribution of these two modes at this point. We see that the field of the two modes are rotational symmetry. So it means these two modes are degenerate modes. So this explains why these two modes can connect with each other at this point. And then we have some patches loaded on both sides of this glide symmetry transmission line. And then we also introduce the asymmetry loading to remove the open stopband in the broadside. These two figures show the scanning performance. We have two bands for the beam scanning. The first band scans 152 degree within 2.2 gigahertz. And the second band has a higher scanning rate. It scans 145 degree within 700 megahertz. Then let me introduce the third technique. It's called coupled resonator feed. Why do we move from this leaky wave antenna to this coupled resonator antenna? If you simply look at the number of the scanning rate, you will know the reason. For this leaky wave antenna, within 100 megahertz bandwidth, the scanning angle usually is less than 20 degree. But if you use this coupled new structure, we only need 50 megahertz bandwidth. We can scan 70 degree angle. So this is really a very high scanning rate. For the design method, we have two different categories, two different structures. So the first category is the waveguide slot antennas. The second is coupled patch antennas. The only difference between the two is for the waveguide slot, you have closed cavity structures. So the radiation is only radiated using these slots. But for the coupled patch antennas, it is an open structure. For the patches, it is open structure, so the radiation happens everywhere for this structure. So for this first structure, we can use the coupling matrix technique to design this antenna. But for the second structure, we need to use a co-design method using the coupling matrix and the characteristic mode analysis. I will introduce these two techniques one by one. Okay, so for the waveguide slot antenna, so this figure shows the architecture for this coupled resonator antennas. So here we have a lot of resonators. So some resonators are radiators. For instance, here 1 and 3, they are radiators. For the second resonator, it does not radiate. And here we also have the coupling between these resonators are different. So here between the 1 and the 2, we use the magnetic coupling. It has 90 degree phase shift. But between the 2 and the 3, we use the electric coupling. It has a minus 90 degree phase shift. Why do we propose this strange architecture? The reason is that this structure can realize broadside radiation at the resonance frequency. So we wanted to realize beam scanning around this broadside within the passband. So that's the reason. This can be understood by checking the phase of these two resonators. As we know, if we wanted to realize the broadside radiation, the phase between the two, difference between the two should be 0. So at the resonance, all the resonator has a 0 phase shift. So the difference between this 1 and 3 is contributed by these two couplers. So one is 90, one is minus 90, so they will cancel with each other. So this we realize the broadside radiation at the resonance frequency. So that's why we propose this strange architecture. And then we model this using a coupled resonator network. So finally, the design is a combination of the antenna problem and the filter problem. Because this structure is coupled resonator, we can model this using coupling matrix. So the coupling matrix include all the information of these coupling values. We can relate this coupling matrix with S11 and S21. This is the filter problem. For the antenna problem, we are interested in the beam scanning. So the beam angle is determined by the phase difference between the radiators. So this is the phase difference. And so we need to also calculate the excitation phase of each resonator using this coupling matrix. So this can be calculated using this equation. So by using a single coupling matrix, we can model both filter and antenna problem. So finally, we can use the coupling matrix theory to synthesize and tune this structure to design a frequency scanning antenna. I will not go to detail for this technique. So let me give you an example. So this is a numerical example, coupling synthesized coupling matrix in the normalized frequency band. As you can see here, S11, S21, they are both less than minus 10 dB. So this means all the energy have been radiated out from this slot, from these radiators. Okay, so this will tells you this antenna has very high efficiency, radiation efficiency. And we designed this coupling matrix in a normalized frequency band. It's called low pass domain in the filter design. This has benefits as we design different frequency band with different bandwidths. For instance, here we are design two different bandwidths, 50 megahertz and 100 megahertz bandwidths at 4 gigahertz. We use the same coupling matrix synthesized to just scale these parameters using different scaling factors. You can achieve the true response. So it means you don't need to design this coupling matrix again. So you can use a single or normalized coupling matrix to design a lot of frequency band with different bandwidths. Okay, so this shows the waveguide prototype, fabrication prototype. We have 5 resonators. We have 3 slots cutting on this waveguide cavity. And this is the measured S11, S21. They are both less than minus 10 dB within this 50 megahertz bandwidth. This figure shows the beam scanning performance. And we can see the efficiency. Efficiency is almost around 80%. So it is very high. And the beam scanning within this 50 megahertz, it can scan around 66 degree. So this figure shows the radiation pattern at different frequencies. So the benefit of this design is it has a very high scanning rate, 66 degree within 1.25% bandwidth. Efficiency is high, around 80%. And later we improve this structure to a uniplanar implementation. This is a very recent work. So we have some topology innovation. So previously we used this alternating electric and magnetic coupling because of the broadside radiation. But for this topology, you need to use a very complicated fabrication to realize this. It's difficult to realize this topology using the planar structure. So we change this to the all magnetic coupling topology. So in this case, we use only a magnetic coupling between all the resonators. But then how about the problem of broadside radiation? So we have mentioned that the reason why we use the alternating magnetic and electric coupling is because of the broadside radiation. But here, if you use 2 magnetic coupling, you will have 180 degree between 1 and 3, right? So here we introduce a phase reversal radiator to this topology. It means for the first and third resonator, they have a phase reversal, pi phase difference in advance. And then as you introduce this coupling, it will have another pi phase difference. This will cancel with each other. So finally, we can realize the beam radiation at the broadside. So this all magnetic coupling topology can be realized using a uniplanar layout. For instance, here this figure shows the planar SLW implementation. So here, all of these magnetic coupling can be realized using this simple window, right? So this structure is very simple. These 2 figures shows the radiation performance. This is S11 and the efficiency. Efficiency is around 60%. And this is the beam radiation pattern at different frequencies. So here the benefits of this new design is it's a purely planar structure. The scanning rate is 70-degree within 1% bandwidth. It's slightly larger than the previous design. And the efficiency is slightly lower than the previous one. It's 60%. Because here we use the planar substrate, it has some loss. If we still use the AL waveguide, we can realize 80% radiation efficiency. Okay, let's move to the coupled patch antennas, this new structure. In this new structure, we need to use the co-design method using coupling matrix theory and characteristic mode analysis. So in this case, we regard this antenna as a two-part system. The input part will feed this antenna. The output is the radiation, receive all the radiations at a far field. So for the far field radiation pattern synthesis, we can use the characteristic mode analysis to do this. And then for the input part, we use the coupling matrix because this is a coupled resonator network. So we can use the coupling matrix to express all the information in this feeding network, including the S11 is the matching, is the reflection at the ports, and also excitation of each resonator using this equation. So we can use a single coupling matrix to express the port reflection and excitation of each mode of this antenna. So we need to use a co-design method based on the two approach. Okay, let me give you an example. So this figure shows the configuration of the coupled patch antenna. We have a lot of patches here, microstrip patches here. And these patches are coupled through both magnetic coupling and electric coupling. So the reason why I use this magnetic and electric coupling is because of the broadside radiation. We have introduced this before. And this is a third order case. So we have three patches here. So the first and second patch are coupled through this inductive magnetic coupling. And the second and the third patch are coupled through this gap. It's electric coupling. Okay, so the first step is we perform the characteristic mode analysis for this structure. So it can calculate all the modes. Here, basically, we have three different modes within this desired frequency band. So by using this mode analysis, we can roughly put all of this resonant frequency within this operational frequency band. And we can also check the radiation pattern of these modes. So we place this all of these modes sequentially in this spectrum one by one. So as we switch this frequency, we will switch the mode from J1 to J2 and to J3. So in this case, you will realize the beam scanning. Okay, then the second step is we can predict this beam scanning by add ideal excitation using a point feed. So this figure shows the predicted beam pattern. As you change frequency, you can realize this radiation beam scanning from left to the right side across this broadside. Okay, but of course this is a very ideal because here the feed is ideal excitation. And the third step is we should replace this ideal feed with the physical structure. Here we use the microstrip line to feed this patch antenna. And then we simulate the S11, the reflection performance, to check the impedance matching. So here we can see the impedance matching is very bad. The S11 is above the minus 10 dB. So this is because of several reasons. I think the major reason is because of in the previous design, in the characteristic mode analysis, we only roughly put all of these resonant modes within this bandwidth, we did not accurately design all the resonant frequencies. As we know for the filter design, if you want to form a very low reflection band, continuous band, usually you should very accurately, very carefully to design each resonance. So the previous design only give you a rough design. So here we need to use the coupling matrix to further tune this resonance. The other minor reason is because of this physical structure. It is not ideal point feed. So we have some perturbations to original mode. So that's the other reason. Okay, then the final step is we can use the coupling matrix to tune this structure to form this low reflection within this operational band. Okay, so this is the fabricated prototype. And this figure shows the radiation performance. The total efficiency is around, I think it's around 70%. And the beam can scan 60 degrees within 100 megahertz bandwidth. Okay, let me summarize this co-design method using the coupling matrix and characteristic mode analysis. Why do we need this so-called characteristic mode analysis method? We have 4 reasons. First, we need to use this method to select the proper modes according to the mode patterns, because here we need to realize the beam scanning, so we need to select the proper radiation patterns, right? And secondly, we can roughly move all the proper modes to the desired frequency band. For instance, here from 2.4 to 2.5, we can put the 3 resonance close to this band. And this method also moves the parasitic modes far away from the operational band. Because for the large array, usually we have a lot of parasitic modes because of the ground plane or the substrate. So we can use this analysis to move this, suppress these parasitic modes. And then we can use this to sequentially place these modes in spectrum for beam scanning. So because here it's a frequency scanning antenna, so we need to switch different modes, switch the beam using this frequency. So we need to sequentially place these modes in the spectrum first. Okay. Why do we need a coupling matrix tuning instead of manually tuning? So why not directly using manual tuning in the last step? It has 3 reasons. So for the narrowband designs, it requires a high quality resonator modes, which are very sensitive to physical parameters. That means if you change any dimension of this resonator, you will have very large frequency shift. And all the resonant modes are strongly coupled with each other. So as you tune the local parameters of the resonator, it will change the global response. So it will become very complicated if you use manual tuning. It is almost impossible to manually tune the response of a very complicated high-order design. If we design a filter, you will know it's very challenging to design and tune a high-order filter. For instance, here we have a 12th order coupled patch antenna. It's very difficult to use the manual tuning to design this. Okay, let me give some imaging and sensing examples. We have 2 different categories. One is the guided wave cases for the very near field application, and the other case is radiative imaging cases. Both of the 2 have 2 different categories. So for instance, guided wave imaging, we have this continuous wave transmission line imaging, and also the discrete resonator imaging. And for the radiative imaging, we have the 1D scanning and the 2D scanning. So I will introduce these imaging examples one by one. Okay, so for the guided wave imaging, here we design a global line. It's a surface wave single conductor transmission line. So this figure shows the singular value decomposition the distribution of this transmission line. And here it shows the experimental setup for the imaging. We place some scatterers above this transmission line. By using a compressive sensing, we can reconstruct the positions of each scatterer. Okay. In combination with the mechanical scanning, we can also extend this to 2D imaging. So for instance, here we have a 2D object. We can reconstruct the shape of this 2D object. We also try some more dispersive transmission lines using the spoof surface plasmon. For instance, here it's a SSP transmission line. We have 3 scatterers above this transmission line. We also designed this hybrid transmission line using the substrate waveguide, integrated waveguide, and spoof surface plasmon. And we place the scatterer above the surface. We can reconstruct the position. We apply this millimeter wave spoof surface plasmon transmission line to the tumor detection, because the tumor has different permittivity from the conventional healthy skin. So by place this transmission line above this skin, we can identify the location of this tumor and identify the shape of this tumor. This is another recent work. It's called a probe-free millimeter wave high-resolution imaging. So here the problem we wanted to solve is to improve the resolution of this imaging by achieve this measurement matrix H using a higher accuracy. So H is very important for the imaging. If it has errors, then the imaging results will have a very big error. Okay, so how do we achieve this measurement matrix H? Usually for this transmission line, we should measure the field distribution in advance. So this H is built by distribution. The millimeter wave frequency, if we use a probe to detect the field distribution, the probe will have perturbation to the original fields, so it will bring in errors in this measurement matrix. So we propose a new technique. It's called a probe-free. It's probe-free way to establish this measurement matrix. Instead of using the measurement to detect this field distribution, we use the simulated or ideal field distribution to build this initial guess for this measurement matrix. And then we correct this difference between the real fields and the simulated fields by using some null positions to correct this. So it means we already know some positions. We can use this data to correct this measurement matrix here. We assume that the real fields are slightly different from the ideal or simulated fields, and this difference can be corrected by updating the single values of this measurement matrix. This figure shows the design of this transmission line. It's a spoof surface plasmon structure at the millimeter wave frequency at a 60 gigahertz. We use a water above this transmission line to detect the position. So here, this shows the reconstructed position. We have very good resolution. So at 60 gigahertz, the resolution is around 0.1 millimeter. Okay, let's move to the discrete resonator imaging. Why do we need to move from this transmission line to the discrete resonator imaging? The reason is that for the transmission line case, usually the bandwidth is very large. But for this resonator case, we can use a very narrow band to perform this imaging. But this resonator case also has drawback. Because of this discrete aperture, the spatial dimension, spatial resolution is not as high as this transmission line case. Okay, so these two figures shows the imaging scenario for this coupled resonator imaging. So we have a lot of resonators coupled with each other. Then we cut some slots. these slots are very small on each on the top surface of each resonator. So these slots are very small, so they don't have radiations. They just couple the power inside this cavity with the outside environment. So as we place an object close to this slot, it will introduce the perturbations to each resonator. So this will produce a frequency shift for each resonator. So here, the challenge is how to extract all the resonator information, especially the resonance frequency of each resonator from the two-part measurement. So usually here it's a two-part system. We just measure the S11 and S21. So we need to reconstruct the resonator information using these two S11 and S21. So here we are still using coupling matrix theory. It provides a good tool to extract this resonator information. So for the coupling matrix, it has all the information of these coupled resonators. So for these diagonal entries, M11, M22, and MNN, so all of the entries represent the resonant frequency shift with respect to the standard frequency. So if we want to reconstruct the information of each resonator, especially the resonance frequency, we need to recover the diagonal entries of this coupling matrix. So here we measure the scattering parameter. We need to recover this coupling matrix, especially the diagonal entries. So that's what we have done in this work. So the coupling matrix extraction method provide a good tool to solve this problem. I will not go to detail for this the technique. So let me show you a proof of concept demonstration. So this is a three resonator coupled with each other. And if we look at the S11, S21, it is very similar to the conventional filter, right? So we have the three resonance for the S11. We have the S21 from this passband. If we look at the S21, it is not very low. This means this coupling aperture does not radiate. It's just a near field coupling. So this coupled resonator is a guided wave. It's a near field coupler. We use this metal strip to test the performance of this coupled resonator. We place this metal strip close to this slot. And then here, this figure shows the recovered image by using the coupling matrix extraction. So we see a good agreement between the two. And we also extend this technique to the 2D imaging by placing these resonators using a zigzag way. So here we use the 9 resonators. They are coupled using this zigzag configuration. And then this figure shows the fabrication prototype for this 9 resonator. We cut a slot on each resonator, on the top surface of each resonator. And this is the metal. We produce a specific metal pattern to test the imaging performance. So we place this object on above this resonator sensor. So this figure shows the reconstructed image using the coupling matrix extraction technique. So we see a good agreement between the two figures. Okay, so this shows the application of this coupled resonator sensor. It is called a radar piano, finished by undergraduate students. So the student used the VIA chip, transceiver, plus the mini circuits coupler to establish, to build a very simple radar. So here we use this coupled resonator as the sensor. It's a one-part system, so we detect the S11. So here, as the finger touch these resonators, it will has different perturbations to the S11. So by using the signal processing, we can reconstruct the position of these resonators after perturbation. So we map each resonator to the piano key. By using this, we can play a song. So this video shows the demo of this radar piano. So as our finger touch this slot at each resonator, it will this will be mapped to the piano key. So we can use this to play the song. Okay, so for this kind of structures, this kind of resonator structures, the drawback is the short distance. Because of this non-radiative slot, that's the one reason. The second reason is all of these slots are separated. So each slot takes charge of a small region. So they are not coupled in the outside, in the surface of this outside. So they cannot generate a very large aperture to increase the distance. Then how do we increase the interaction distance? Because we wanted to use this kind of resonator for the high-gesture recognition. Can we simply increase the slot size to make it radiate? The answer is no, because if we increase the size of the slot, all the slot will radiate, then the quality factor of the whole resonator, all of this resonator, the quality factor will decrease. Then the frequency diversity, frequency sensitivity of the whole system will decrease. So the performance will be degraded. So we have another project. It's multi-mode resonator for this sensor. It's also an undergraduate student project. So instead of using the single mode resonator by sequentially coupled this single mode resonator, we use a multi-mode resonator. We design a very large cavity, and we cut some slots on top surface of this large cavity to introduce the interaction between the cavity and the outside environment. Because all of these slots are coupled, have strong coupling between each other, both inside the cavity and also outside this cavity. So the aperture, interaction aperture, is very large. So in this case, the distance of the interaction can be increased. Then how to solve the trade-off between the interaction distance and the quality factor? Still, we need to face this challenge because here, as we increase the number of slots, the interaction will increase, of course, because you will have some more radiation, but the quality factor will decrease. Then maybe the performance will decrease. So you will have a balance. You will achieve a balance between the two. So in this design, the focus of this work is to propose some methods to determine the optimal number of slots and their positions for this multimode cavity. Then we go back to the original sensing equation. So the measurement matrix, the sensing capacity actually is the ultimate goal to be maximized. So we can use the capacity as the optimization goal to determine the optimal number of slots and their positions. So this figure shows optimized design for this multimode resonator. Finally, we found that by using 8 slot cutting on the top surface of this cavity, we can achieve the best performance. As we further increase the slot number, the sensing capacity will decrease. So this figure shows that the balance between this interaction and the quality factor. And this figure shows the signal to noise ratio of this sensor. So as we put our hands in front of this the sensor, if you change your hand with different gesture, you will have a perturbation to the S11. You will measure this delta S11. So this signal is almost around -40 dB, right? And the noise level is below -70 dB. So we have at least a 20 dB signal to noise ratio in this sensor. And then we apply this sensor to the high-gesture recognition. So if we look at the sensing equation, H rho equal to gamma. for the imaging problem, we need to solve this role, right? But for this sensing problem, it's different. For the sensing and the classification, we don't need to solve this role. We only need to classify different role. For instance, here we have 10 different head gestures. So this represents 0, this 1, 2, 3, 4. So we have 10 different head gestures to classify. So in this case, we don't need to solve the accurate role here. We just do the classification problem. This is much simpler than the imaging. So here we use the convolutional neural network to solve this classification problem. These two figures shows the classification results. This demonstrates that we can identify, we can classify these 10 head gestures using this sensor. Okay, let me then introduce the radiative cases in the imaging. So the first case is the 1D scanning liquid antenna for imaging. So this figure shows the imaging scenario. We have this 1D scanning antenna. So here we use the liquid wave antenna. It's a hybrid SRW and SSPP structure. This figure shows the scanning performance. It scans 70 degrees within 500 megahertz bandwidth. So okay, so this figure shows the experimental setup for this imaging. We have the scatter in front of this transmitter and receiver. This is the liquid wave antenna. This shows the imaging results. We can identify the single scatter and the wide scatter and the thick scatter and also the double scatters. So the minimum distance between the two scatter is 0 point spatial wavelength. This example, we use this frequency scanning antenna to the degree of arrival in the wireless communication. I think this application is very straightforward because for the liquid wave antenna, we have a one-to-one correspondence between the frequency and the beam angle. So we can use this frequency to identify the direction of arrival in the wireless communication. So this figure shows the antenna that we use is a waveguide slot antenna. So this shows the beam scanning performance. Here, this table shows the experimental results by using this antenna. This left column is the ideal angle. So this is estimated angle using this algorithm. As we can see here, it has very good accuracy. This is a very recent work. We use frequency scanning antennas to the imaging, to the integrated sensing and the backscatter communication. So here we use the frequency scanning antenna as the transmitter and the receiver. This figure shows the antenna that we use is a coupled resonator slot antenna. This figure shows the radiation patterns. So it scans 70 degrees within 50 megahertz. The center frequency is around 4 gigahertz. Okay, so here we place two scatters in the near field of this antenna. One is the cluster scatter, one is the tag scatter. So for the tag, it can modulate the reflection phase using the BPSK scheme. So for the sensing, we can reconstruct the positions of the two scatter, and also we can identify which one is the cluster scatter, which one is the tag scatter. So the signal processing is very straightforward because the cluster scatter is different from this tag scatter. The cluster scatter does not change, it's static. But for the tag, it changes with time. The reflection phase is changing. It's modulated using the BPSK. So we can identify which one is the cluster, which one is the tag. Okay. We also use this tag to do the backscatter communication. So this is the bit error rate for this communication result. we compare this with the theoretical result of BPSK, so we can see it is very close. So this example shows this example validates the possibility using this frequency scanning antenna for integrated sensing communication. This is another application. We use this frequency scanning antenna for multi-target localization and monitoring. These two figures shows the coupled patch antennas. This antenna can scan 80 degrees within 100 megahertz bandwidth. So the first example is the localization and the tracking example. The human person is moving at different locations from L1 to L4. Then by detecting the normalized breath energy of this human person, we can localize this person in different locations. So this shows the normalized breath energy in the spectrum, because the frequency scanning antenna has a one-to-one correspondence between the frequency and the angle. So from this spectrum information, we can determine the angle of this target. So this is the basic principle. The second example is we have three person. We can simultaneously track these three person. We can localize the three targets using this antenna. And the third example is respiration monitoring. So we have a single target sit still here. We want to monitor the respiration. We also have another moving person as interference. So for the conventional antenna, if it is omnidirectional antenna, these two signals will be mixed together. You cannot separate the two signals. But here we can use the beam scanning by control the frequency to shoot the beam to the target, and meanwhile we can suppress the interference from this moving person. So this figure shows the respiration results. These are two videos shows the multi-target respiration monitoring use this new antenna. We use the VNA as the transceiver. We can monitor the respiration of these two targets, two person in real time. So these two figures shows the respiration, and if this video shows the one interference with one target, so we can suppress the interference and monitor the static target for the respiration monitoring. Okay, then let's move to the 2D scanning. How do we extend the 1D scanning to the 2D scanning? The most simple way is we can use the MIMO liquid wave antenna. So we design a lot of liquid wave antenna and use different ports to connect with the MIMO system. So we scan the beam in this horizontal direction by using the frequency due to this liquid antenna. And in the vertical direction, we can use the digital beamforming using this MIMO transceiver. So this can realize the 2D scanning. That's the most simple way. By using this 2D scanning system, we can image the 3D objects. But this system is very expensive, as we have introduced before. So can we have some low-cost design using a single port system? So this is a very recent work. Instead of connecting all of these antennas using the MIMO system, we use a multiplexer to combine all of these antennas to a single port. Then we design different frequency bands to connect with each antenna. So different antenna works on different frequency band. So we use the frequency diversity to scan the beam in both vertical direction and this horizontal direction. So for the single frequency scanning antenna, it can scan the beam using the frequency. And then in the horizontal direction, we can switch each antenna by control the frequency band. So it is it is very similar to the MIMO. So the imaging principle is very similar to the MIMO. We just use the frequency to control the excitation of each single antenna. So this shows a 4-channel design for this multiplexer. So we connect the frequency scanning antenna at each channel of the sub-frequency band. So this is the fabrication prototype for this 4-channel frequency scanning antennas. And this shows the imaging result as we place the metal scatter at different positions in this 2D plane. We can localize the position, and also we can detect the shape of this metal strip. So this video shows a real-time imaging using this single antenna. It's a single input and a single output system. We use this VNA for the transceiver to connect with this single input and a single output system antenna. Okay. And this is a recent work. We replaced the multiplexer using power divider. Because the multiplexer is very difficult to design, so we wanted to replace it with a power divider. Then how do we produce the diversity in this direction? Because if we simply using power divider to connect antennas, you cannot achieve the frequency diversity in this direction. So here the strategy is we introduce some random phase coding to each antenna. So for instance, here is a 16-channel design. Here is the single input part to using this power divider to expand it to 16 ports to connect with 16 sub-antennas. So for each antenna, it's frequency scanning antenna. And meanwhile, for each antenna, we have some phase coding technique. It's a random phase coding technique. So all of these 16 channels have slightly different with each other. So this figure shows the correlation between the 16 channels. We can see that by using this random phase coding, the correlation between these channels are not very high. So this shows the imaging system set up. We place this antenna in front of this object. We can reconstruct the position and the shape of this object. This shows the imaging results. We can use this metal strip at different locations in this 2D plane. And this is 2 metal strip, and this is also a 2 metal strip. We can reconstruct the shape roughly. Okay, this is another technique using dispersive metasurface. So by using the metasurface, we can also extend the 1D to 2D scanning. So this figure shows 1D scanning, beam scanning metasurface. As we know, for the metasurface, the beam angle is determined by the phase gradient of this metasurface. So if we design frequency-dependent phase gradient for this metasurface, it can generate the beam scanning using the frequency. So the 1D scanning is very simple. And then how do we extend this 1D to 2D radiation? So the principle is very similar to the previous one. We introduce the random phase coding to this metasurface to extend the frequency diversity to the whole 2D aperture. So these 2 videos shows the 1D and the 2D tracking for the moving object. The first video shows a moving strip. As we move the strip at different locations, we can continuously track the positions. And this figure shows the 2D tracking of the swinging ball. So this is 2D imaging result. So the position of the ball is in the 2D plane. So by using this dispersive metasurface, we can track the positions of this swinging ball in real time. Okay, finally, let me conclude this talk. In this talk, we introduced the frequency diverse microwave imaging and sensing. So we introduced the principle and the dispersion enhancement techniques. And also I give some examples of guided wave imaging and examples of radiative imaging. Okay, thank you for your attention.